Welcome to another statics video. We are looking at chapter 5 in the textbook, and we are going to be looking at frame analysis in this chapter. So we have already looked at truss analysis, and while frame analysis and truss analysis have some things in common, they're also quite different. So the main distinguishing feature between a frame and a truss is that when we looked at trusses, we assumed that all of the connections of all the internal members were pin connections, and that none of the internal members carried any kind of bending stress. There were no moments applied to any of the members. And anytime we applied an external load, we assumed that that load was being applied at a joint. Frames, on the other hand, can have loads applied to them at any point. And what happens is when a load is applied between some of the joints, it causes bending to occur. And that bending results in various types of bending stresses. So that's the main distinguishing feature, is that a frame can have multi-force members, forces that are subjected to compression, tension, or bending. Whereas in a truss, all of the forces are either causing compression or tension. All of the forces are axial. So because a frame can carry bending stresses in its members, we are not going to be looking at the loads or stresses in the members themselves. That type of analysis is a little more complicated than this class will allow. It's beyond the scope of this class. So instead, when we analyze a frame, what we are going to be analyzing is the forces that are acting on the frame joints. So the process is going to start off the same as truss analysis. We are going to first look at the external reaction forces, or at the supports. And there may be some missing geometry that we need to find, but once we have the missing geometry and the external support reactions, then we can begin analyzing the frame. And the way that we do that is not by a method of joints like we did with truss analysis, but instead we are going to look at each structural member individually and draw a free body diagram of it and calculate the reactions at the ends or joints of that particular member. And once we have found what those reactions are, then we can move on to the next member. Now, another thing about frame analysis that makes it a little different from truss analysis is that in truss analysis, when we analyze one joint, typically we were able to find all of the missing forces before moving on. With frame analysis, depending on the loading and the geometry of the frame, we may not be able to find all of the missing forces. We may still have some missing forces that are unknown and will remain unknown until later on in the process. So after analyzing one individual frame member, we might need to move on and still have a few of those forces unknown. But eventually we will find the key piece of information we will need that will allow us to go back to that previous frame member and essentially fill in the blanks. And then eventually we will complete the analysis, and just like with truss analysis, we will be able to check our work. We'll be able to look at the overall forces and make sure everything is canceling out as it should due to static equilibrium. So again, the thing we need to keep in mind here is that with truss analysis, we considered how are the truss members affecting the joints. And we need to sort of flip that thought, and when we're looking at frame analysis, we need to think the other way around. How do the joints affect the frame members? And so it's not perhaps as simple as truss analysis. As I look at this diagram I have here, I don't know that it's quite this simple here with a joint pushing out in both directions. We can't necessarily say it's in compression, but what we can say is that if a joint is affecting one frame member in one direction, like here horizontally to the left, then it is pushing against the adjoining frame member in the opposite direction. So it's pushing out in both directions, or it's pulling in both directions. So I don't know that it's technically most accurate to describe these joints as being in compression or tension, but the important thing to recognize is that the adjacent or adjoining frame members are affected differently by the joint that connects them. If the joint is pushing this frame member to the left, it's pushing the other one to the right, and so on. Same thing in the vertical direction. If it's pushing one up, it's pushing the next one down. I think this will make more sense when we see it in practice. So here is a frame. We have a vertical column supported by this pin reaction at A. At B, the support is going to prevent it from moving further to the right, it looks like. We have a load applied at the end of this horizontal boom, and these are all pin connections. So the only thing that's going to prevent this boom from swinging down when we apply this load is this brace. This brace is connected partway across the length of the boom and partway along the height of the post. And so what we want to do when we analyze a frame like this is basically just to find the joint reactions. How are these joints pushing against the structural members? We do not need to find the forces in the structural members themselves. Now, in addition to the externally applied load of 10,000 pounds, we are going to consider the weight of these framing members. The problem statement tells us that the post weighs 1,400 pounds. So we want to consider that weight. You can think of the weight of a framing member as being applied at its center. So if this is 10, 12, 14 feet tall, this weight would be 7 feet up. Now that doesn't really matter in this particular case, since the weight is going to pass directly through support A. It's not going to cause a moment, but it's going to come straight down here and be 1,400. The boom is 1,500 pounds. So the boom is the horizontal member, and so it is going to have a weight. Now, in this case, the location of it is going to be significant. We've got 10 and 4 is 14 feet. Half of that is 7. So what we're saying is at a point that is 7 feet over from the post, we will have a weight acting straight down of 1,500 pounds. And the brace is 900 pounds. So again, in its exact center. Now, the distance from the post to where the brace connects to the boom is 10 feet. So half of that is 5 feet. So it's going to be 5 feet over. We'll have that weight of the brace, which is 900 pounds, acting straight down. So because we are including self-weights, it's not quite as simple as it appeared initially. It looked like we only had the one load here of 10,000 pounds. It turns out we actually have 4 loads. So we want to calculate reaction forces. There's going to be a vertical reaction force at support A and a horizontal reaction force there at A as well. And actually, I think that's going to go the other way. I think the sense is going to be the other direction. There we go. And I'll explain in a moment why that is. And at B, up here, there's going to be a horizontal reaction to the left. So why did I assume that that was the sense here? Well, there are no horizontal applied loads to this frame. So why would there be horizontal reaction forces? Well, all of these weights and the external load applied here are all trying to pull this whole frame down. It's going to try to make the whole thing rotate clockwise. So in order to prevent that, in order to prevent this crane framework from toppling over to the right, something has to be pushing back to the left. And the problem statement tells us support B has one horizontal reaction. So that horizontal reaction has to be going to the left to prevent failure, to prevent structural collapse. And if this reaction force is going to the left, then the reaction at A must be going to the right. So let's find what that reaction at B is by summing the moments about A. If we sum the moments about A, we'll have that reaction at B in the x direction multiplied by its moment arm distance of 14 feet. And that's going to be pushing it back in a counterclockwise direction, so that's positive. These other three forces are all going to cause negative rotations, negative moments. So we've got negative 900 times the horizontal distance from A to 9 is 5 feet, minus 1500 times its horizontal distance here was 7 feet, because the weight is at the midpoint. The boom is 14 feet long, half of 14 is 7. And we also have the 10,000 externally applied load multiplied by a distance of 14 feet. So the reaction at B in the x direction is going to equal 900 times 5 plus 1500 times 7 plus 10,000 times 14. And then all of that gets divided by 14. So I found that RBX is equal to 11,070 if I rounded my 4 significant figures. That's how many pounds it is. So if that force is pushing to the left, then the reaction at A in the x direction has to be the same thing, but going in the opposite direction. Now I could label this as negative, or just by drawing the arrow to the left, that indicates the direction as well. So I'm not really worried so much about sign, plus or minus signs, when doing this type of frame analysis, because we've got the diagram to show us the directions of the forces. And then to find the reaction at A in the y direction, we just have to sum the forces in the y direction. That will equal 0. And so we've got 1400 going down, 900 going down, 1500 going down, 10,000 going down, plus RA in the y direction. So if we solve that equation, we should find RA in the y direction is 13,800 pounds. So now we found our support reaction forces. It's time to start the frame analysis, and we will do that in the next video.